Hello, today I'm here to walk you through the diagnosis of a real-world SQLite issue using Live Recorder and UDB from Undo. This is an old issue which has already been resolved, but we shall work through it to see how it could have been diagnosed using time travel debugging without any understanding of the SQLite codebase and only general programming expertise. If you wish to reproduce this is ticket 81A7F7B9 found in SQLite version 3.30.0. So let's begin by downloading the source code for the 3.30.0 release of SQLite. With the download complete, we can now extract the source code. We can see SQLite uses configure, so let's set some C flags to make debugging easier, i.e. -g gdb and -o0, and configure the build process. And now let's build it with make. Fortunately, that didn't take too long to build, and we can see from the final link command that we output a binary called SQLite3. So let's launch that and we can attempt to reproduce the issue from the ticket. As expected, we can see we have version 3.30.0 here, so hopefully this is the correct version to reproduce this issue. So back to the ticket and we'll start copying in these SQL commands. So let's copy the final command, and we see the error. So we've confirmed we have the correct code base to start diagnosing this. In order to save ourselves some time, let's copy all of that SQL into a file that we can use going forward. And now we've got this file, let's just check that we can run it through SQLite and reproduce the same issue. As we now have a simple way to reproduce this bug, we can capture a recording of it with Undo's Live Recorder tool. We'll then be able to use this recording to start diagnosis. We have recorded SQLite reproducing the error and saved this to a file in the local directory. This recording file contains everything needed to deterministically reproduce the error and is 15 megabytes. In order to debug SQLite, I have opened the workspace in Visual Studio Code. As you can see, I have the SQL file that we created copied from the website, as well as the shell.c and SQLite 3.c source code files open. And in the directory structure, we can see the recording file that we've just generated. Having the full application in just 2 C source files suggests there is some packaging done when the application sources are shipped. We can see shell.c is 19,000 lines of C code long. And if we actually look in SQLite 3.c, we can see it's even longer at some 225,000 lines of C code. In order to debug our issue, we can go to the Run and Debug panel, where we can select UDB replay a live recorder recording. We can launch that and we will be asked to select the recording file that we've just generated. And as this launches, we will see it stop at main automatically, and we can ignore that exception as this is the beta integration with Visual Studio Code at this point. As you can see, in addition to the usual continue, step over, step into, step out, as well as the restart and stop controls, there are a plethora of additional controls provided by undo. These are the reverse continue, reverse step over, reverse step into, reverse step out of, as well as go back to start, go to end. We also have a go to timestamp option, as well as a set bookmark which we would subsequently be able to use to go to that bookmark. And finally there is the undo button which allows you to undo the last navigation operation. So let's continue from here to run the application, and we see the SQLite error message in the terminal window at the bottom, as well as an error that's popped up because we don't have the standard library sources installed on this system, but we shouldn't need those today anyway. We can see in the call stack that we are currently in the exit function, and this is because the error did not actually cause the application to crash, so it terminated normally. So we will have to go back to where this error message came from. And we can use the Debug Console tab to access the UDB console, which is based on GDB. As you can see in the console, the program has stopped and we have reached the end of recorded history, as we're at the end of the recording file. However, due to a quirk of the way Visual Studio works, you need to prefix any command you wish to issue with -exec. So let's use the -exec ugo event previous name equals right command, which will cause the replay engine to run backwards in time until the last time something was output from the application. We can see this confuses the IDE a little bit, but we can ignore that for the moment. In the call stack, we are in the glibc write function, and we can have a look at the parameters that were passed to that, just to verify it. So we can do -exec info args to verify the arguments provided to the write function, and that buffer is a pointer, so let's try and print that string out. We'll have to cast it to a char star because the buffer is actually a void star in this function. And as we can see, that's the error message that we've seen in the console. So we're at the right place. At this point in time, the application has stopped just as it output that line to the console. So we're currently deep in libc. So let's go up the call stack to the last function from our application. And here we can see we're at the printf line in the code. We can check the parameters that are passed, and we can see that this one is an array of characters with error near line 5. And the actual error message, database disk images malformed. We have a look further upwards, we can find the actual SQL command we were trying to execute. Insert into VT0, the value's integrity check. So this is the command that we wanted to explore and diagnose why this caused the failure. We can take advantage of the fact that we are trying to run an integrity check function. So if we search for the string integrity check, we can see if we can find that function. Unfortunately, we don't have any instances in shell.c, so we'll have to have a look in the SQLite 3.c. 21 matches, that's a good start. Have a quick look. We're hitting them in comments. So since we're looking for a string, let's try putting some quotes in the search string. Much better. 2 instances. The first one, there's a do integrity check function, so we'll put a breakpoint on that. Check the second one. We have another storage integrity function. We'll put breakpoint on both of them so we can see which one it is. And now if we do a reverse continue, we'll go back in time, and it turns out it was the second one that we hit. So we've stopped just before this function call. We can see that the return code at this point is 0. If we step over, then the return code we see is now 267. That certainly seems erroneous, but let's see if we can see how these return codes are defined. So let's have a peek. And we can see that 0 would in fact have been success, so a 267 error code is not what we're looking for. we have a scroll down, we can see that there are error codes up to 100, and then there seem to be some higher order error codes with bits shifted left 8 into the second byte. So we've got 267, that's 256 plus 11. We can see 11 suggests that something is corrupt. That's a good start. That's the sort of issue that we're looking for, and that comment looked a lot like the error code. And we saw 267, so we're looking for 1 shift left 8. It's even nicely highlighted for us, so we've got the vtable is corrupt. That's the error message that we were looking for, so it looks like we found the correct function call, where we found the bad error return value. So now we've confirmed that this function is returning an error. What we can do is we can step backwards into the function and find out where that value came from. And so we're at the end of the function, so we're going to step back a little more to see if we can find where the RC is set to 267. See it is here. And it seems to have been set by this index integrity check function. So what we can do is we can step over it to after it is set, and then step backwards into this function to see where the actual error was detected. So at the end of that function, we're going to need to step backwards to see where the return value came from. Could possibly be inside function call. So let's just do a reverse next and confirm yes, it was inside that function. So that's where the actual value was returned from. So we're going to need to go into that function to see. Or do I step into? Is it proves to be a fairly small function, so this is a good place to explore. And that does indeed appear to be where the 267 value is coming from. What we can do at this point is we can set a watch point on this p-rc value to see where the value is set in this data structure, as that's probably set sometime earlier. And then we can run backwards to see where that value is set, which hopefully will be where the error was detected. That seems to have worked. We can ignore that exception because that's just Visual Studio Code not knowing what a data watch point is. And we can see that the FTS5 corrupt value is being stored as the return code here. So this does indeed appear to be the right place. So let's see how we've made this decision. IOF is currently set to 4. Endbyte is set to 11. We can also see that in the top left. The size leaf value is also 11. So yes, 4 plus 11 is 15. That's greater than 11. That's correct. So we have to figure out where these come from. So endbyte is an automatic variable that's just been declared on the stack. It looks like it must be being set in this function. We can just have a quick peek to make sure it is being passed as an address. Yes, it is. So this function has a side effect, presumably, of updating the second parameter that's passed to it. You can see there. So this is reading a variable length int off a stream of data, which presumably that's the pointer to. The IOF would be the offset in the stream. We're going to increment that by the size of the variable length int, and the value being written back is 11. So we would presumably increment that by 1. Let's go back and just double check this. So here we are before. IOF is 3, so that would be an offset. And endbyte is whatever value is on stack because it's only just been declared. Yeah, we step over that. We can see that we do have the 4 and 11 values that we've been using. So that seems to be reading the data in from the data stream. That accounts for the first side of this. I guess the next thing to do is start looking at where the size leaf came from. So size leaf is 11. Let's have a look at this data structure. You can see the values in there, but I think let's try and actually look at its definition to see what these members are meant to be. This may take a second. It's a huge file it's searching through. And here we are. So we have this FTS5 data. We see we have a pointer to the buffer containing the record. NM is the size of the record in bytes, and size leaf is the size of the record without the page index, which typically page index would be a small thing, so size leaf probably should be large but still slightly smaller than NM. Let's go back and have a look at what the actual values were again. And we see size leaf is 11 and NN is 65,568, which is slightly bigger than 64K, 65535, which is getting me slightly curious. So let's set a watch point on this size leaf value, and then we'll be able to run backwards in time to see where this value was set, because this 11 is starting to look suspicious to me. So we've set the watch point. We can now reverse continue from here. And here we are. Ignore that exception again. We see size leaf is about to be written. So FTS get uint16, that's reading the uint16 value from a char star pointer. So reading in a byte, shifting it, reading another byte. That is a 16-bit value. This gets me even more curious because, let's say, we're near 64K, and 64K is the largest number you can store in an unsigned 16-bit value. So I'm now starting to be very suspicious of this 11. I think the next step that we're going to have to look at this data and see if we can figure out where this 11 actually came from originally. So let's cast this to a char array and then to reference the pointer so we can actually see the data in the watch window here. If we expand this, we can see the individual bytes. As we can see, byte 2 is 0 and 3 is 11. It represents the 16-bit value we were looking for, just to double check. The first value is indeed the one that gets shifted, so 0 gets shifted, that's 0 plus 11. That's how we get our 11 value. Which means this is the byte we're interested in. What we want to do now is figure out where this was written. So the first thing we'll do is we'll disable the existing watch points because we won't be using them anymore as we're about to travel further back. And we don't want to hit any random watch points which are no longer relevant. We'll set a new watch point at precisely this address. So we're setting the watch point as exactly the address of the 11. And then we can do the reverse continue yet again. We can ignore this error. This is because we don't have the standard library source code. But if we look in the call stack, the copy payload function is doing a mem copy. So this is copying from p payload into p buff. So let's repeat what we've just done and add the p payload data to the watch window. So we can find out where the actual value of 11 is. It may be at a different offset in this mem copy. Can make this window bigger so we can see more of this. And it seems that the 11 is indeed in the same place, so an offset 3. This means we can disable watch points again, because we don't want to have any old watch points in addresses that are no longer relevant. And we'll set a new watch point for this address. I have to cast it to a char star because I don't know what that pointer is, to be absolutely certain that we definitely get the right address. And now that watch point is set, we reverse continue again. It looks like we've hit another library function, so probably another mem copy. Let's have a look in the call stack. Yep, so we're copying p cell to p data. Let's add that again to the watch list so we can see where the 11 value is. Let's expand it. Okay, looks like there's more header information in this memory copy. Scroll down. That looks like the start of the table we're used to, so byte 17 is the 11. So we can basically repeat what we've just done. We'll set a breakpoint at the P cell byte 11. First, let's disable the existing watch points again. And then set that breakpoint. Again, we'll just cast the pointer just to make sure we'll definitely get it the right address. Okay, so let's reverse continue. Looks like another mem copy. Close the warning, look up the call stack. Yep, it's another mem copy. Technically we have a P payload here, but that's not going to be what we're looking at. What we're interested in is the P source. So let's add P source here. And again, let's expand it. Okay, that's not quite as much additional header. It looks like we're byte 8. So, repeat again, disable the existing watch points. Set a new one at P source 8. Now that's set, let's reverse continue again. And yet another mem copy, it seems. Look up the call stack again. It is indeed a mem copy. It's starting to look slightly more interesting. Maybe getting back to where we want to be. So let's add this pmem-z. And we can expand this. And we'll see we're at offset 3. So it's starting to look more like the table without any header. Again, we'll disable the watch points. Set a new watch point at the address we're interested in. And again, we can reverse continue. Okay, we've hit the watch point arrow, we can close that. Interestingly, we now seem to be in a FTS5 put U16, which is where we write the value. We are indeed writing value 11, so we found where this value is written. We can go back up the execution with a reverse finish, and we can see where we're being called, and here we have our problem. Someone's tried to write 65,547 into a U16. Since the maximum is 65535, that wraps round and we get the value 11. So let's just print out this value as hexadecimal so we can see why it won't fit into an unsigned 16. Unsigned 16 is a 16-bit value, therefore it can be stored in 2 bytes. We see here 65547, the low order 16 bits are 000B, which is indeed 11, with the 1 in the 17th bit, which will not fit and gets stripped out when it is cast to an unsigned 16. So now we know we're trying to store an oversized value into a U16. We can set a watch point on the page-buff.n to see where this value came from. Disable the existing watch points, we'll just set this new one. And with that watch point set, we can now reverse continue to see where it came from. Again, ignore that exception. It's apparently modified in this line, so let's just have a look at what this is. Okay, it's a macro, so it is modified here. We can see at the bottom that pbuff-n is updated with the third parameter added to it. If we look in the code, we can see that the entire doc list will fit in the current leaf, so that suggests we believe it'll fit. Look at the test above, see that it's being compared to this page size value, so that's 70,000. 70,000 is too large. That's why we're allowing this to happen. So let's see, where's that 70,000 come from? Scroll up and see. Okay, so page size is constant int and it's coming from a configuration structure. Let's set a watch point on the configuration structure and we'll see where that was loaded with this 70,000 value. And again, we can reverse continue now we've got this watch point set. Okay, ignore that exception again. So we can see here that we're setting the page size for a value that's passed in, but a comparison has been done to make sure it's not less than 0 and it's not greater than the FTS5 max page size. That is a problem because the max page size, that's going to allow 128 kilobyte pages, which won't work when you've got unsigned 16-bit offsets. You can't have values larger than 64 kilobytes. So we found our root cause. This is the problem. This is why the application finds there's an integrity error, and ultimately where this problem has come from. So this PG has said 70 values, page size. I think it's coming from the SQL, because I recall, yes, the second line, you can see it's explicitly being set. So maybe this SQL would never work, but ultimately SQLite should detect it, and it should be caught by having a max page size that is actually possible to implement with the data structures they have. So I think we've found why this test case and why this ticket causes the failure we see. We have a pretty good idea of how we can fix it as well, i.e. we can set that max page size to 64K. So now let's go back to the original ticket. If we have a look at the details, we notice it's closed, so it has been fixed. Does the history give us any information? That just shows that it was closed. Maybe the timeline. Ah, yes. This shows that the correct fix is to disallow the FTS5 page sizes greater than 64K, which is exactly what we predicted. And we have a check-in for this, so we can have a look at the code change. And there's a test at the bottom, but the actual code change is exactly as we saw. The definition, just zoom in so we can see it more clearly, is being changed from 128K to 64K as the max page size. Hopefully you can see how I've been able to use time travel debugging analysis of this application failure, and without any real understanding of the actual SQLite application, I was still able to follow my way through and find the root cause and in fact the fix that was originally implemented, purely by setting watch points and running backwards until we could find where this bad data was coming from. Hopefully this will give you some ideas how you can use time travel debugging to help you on your applications in the future. Thank you for your time.